Hey there guys, today I'm going to talk to you about cross products, or otherwise known as vector products. And so you might remember last time we were talking about scalar products, also called dot products. And so what that did was that took two vectors, vector A and B, and you would dot them together and the output would be a scalar, hence the name scalar product. Um, The vector product is somewhat similar, somewhat analogous, but it's also quite different because the output is going to be not a scalar, but actually a vector output. And so I guess the first way that I want you to interpret this is to consider it as an area. It's going to be the area of the parallelogram. So if we have our two vectors, A here, and we're crossing it with B, you write them like this. You write A cross B like that. Well, the formula that you're going to get out, which I'll actually prove for you next time, is that it's going to be the length of A times the length of B times the sine of theta, where theta is the angle between them. Now, don't get this confused with the dot product formula, which was the length of A times the length of B times the cosine of the angle in between them. Similar, but very different in their implications. And so to interpret this geometrically, like I said, this is the first way that I want you to consider this is an area. And so if you come over here and look at this picture, well, we have these two vectors. So we have A. A is going to be this vector that goes along here. We have our vector A, and then we have our vector B that comes along here. And we're going to cross them, and you can see there's the angle theta that's in between them is right there. And then this other term here, this h, is just I drew down a perpendicular line. So this is the line going straight from the top of A to intersect perpendicularly with B. And so if you just believe me for now on this formula, this one that's up here, if you'll just trust me on this for the moment, and I'll prove it for you next time, then I can show you that that you can actually interpret this as the area of the parallelogram, where by the area of the parallelogram, I mean if you were to take these two vectors and turn them into a parallelogram, such that up here this is, well, if I can write neatly here, this is B up here as well, sorry about that, and this is A here, and we've just created a parallelogram by moving the vectors from one point to another. And so if we consider the area now of a parallelogram, then it's going to be the height, that h term there, and it's going to be that multiplied by the b vector. And to visualize this, you can consider taking this term right here and moving it over here, and it turns out that this is going to be perfectly work out such that the area of a parallelogram is going to be h times the length of its bottom side, the length of b. And now I want you to take a look at this sine theta term. So if you remember your SOHCAHTOA from middle school, then the sine is going to be the opposite over the hypotenuse, the angle opposite over the hypotenuse, or not the angle opposite, the side opposite. So in other words, our sine theta, sine of theta, if you look at the picture, is going to be sine theta equals, well, opposite is h, so that's h, and then the hypotenuse here is just the length of A, the length of A. And that's not going to be the vector A, it's going to be the length of A. If you think about having a vector is the magnitude and the direction, but when we're looking at the area, all we want, or when we're looking at the sine, all we want is the magnitude of that vector. The direction is not quite so important. And so we have the sine theta equal to h over the length of A, and now we can actually plug that back into the formula on top, and we can get that, finally we can get that A crossed with B, so A cross B here is equal to the length of A, so the length of A there, times the length of B, times the length of B, times plugging in for the sine theta, we're just going to have h divided by the length of A. And I'm sure you can go ahead and see now that we can cancel this term here with this term here, and what we'll actually be left with is just h times the length of b. So h times the length of b, which tells us that the magnitude of the cross product is actually equal to the area of the parallelogram. And that's an important thing to remember. So the magnitude of A cross B, so if you're looking at just the magnitude, not considering the direction of the vector, but just the magnitude of the vector, it is going to be equal to the area of this parallelogram that I'm circling here in blue, where we have the parallelogram created by the two angles. And all right, now so let's look at a couple properties of the cross product. So the biggest one that I want to point out that's actually different than things that you may have seen in math before is that A crossed with B, so A cross B, does not actually equal B cross A. What it equals is minus B cross A. B cross A. And if you guys have had linear algebra, that's because when you swap two rows when you're taking the determinant, that'll flip the sign. And if you haven't had linear algebra, don't worry about it. I can do a video on it specifically if there's enough interest. But for now, just take my word on it. And the rest of the properties are fairly straightforward. It's going to be just a typical A crossed with B plus C, where these are all vectors, and this is going to equal A cross B plus A cross C plus A crossed C. And you would expect this from the distributive property. So this one's intuitive, and then the last one is going to be n times n is being a scalar out here. So you could write this as n. You could write it as alpha. You could write it as any scalar. So n times A cross B is going to equal n A cross B, and moreover it's also going to be equal to A crossed with NB. So again, this is a fairly straightforward property that you are, I'm sure, familiar with. And one last thing that I want to point out to you, though, is that if you have a vector crossed with itself, so if you have A cross A, well, let's look at what this is going to equal. And just briefly remembering, if you can recall that formula, it's going to be the length of A times the length of A times the sine of theta, where theta is the angle between A and A. Well, that angle is going to be 0, and sine of 0, I don't know if you remember this from your unit circle, but sine of 0 is just 0. If you don't, you can derive it or look it up, but sine of 0 equals 0. So what this means is that anytime we have a vector and we cross it with a vector that is either parallel to it or the exact same vector, well, this is just going to end up being 0. And like I said, the biggest one to notice is this minus sign here, and we can really briefly here look at actually how to compute a cross product. And I say briefly because I'm not going to go into all of the linear algebra as far as what a determinant is and how to take it, but I will show it to you in case you've already had it. So let's go ahead and clear this if you want to see how to compute a dot product, or a cross product, sorry, a vector product. So if we have A cross B, well, what we're going to do is we're going to set it up as a determinant. This is the easiest way for me to remember the formula. There's also a formula which I'll present to you at the end here for how to do this, but the easiest way that I find to remember is to set it up as a determinant between I hat, j hat, and k hat, where I hat, j hat, and k hat are just typical unit vectors, where I hat is the one in the x direction, so I hat would be, I guess, 1, 0, 0, j hat would be 0, 1, 0, and k hat would be 0, 0, 1. So essentially I hat corresponds to the component along the x direction, j hat the component along the y direction, and k hat the component along the z direction of a Cartesian system. And so then what we're going to do is we're going to have our ax component here, and our ay component here, and our az component here, and then similarly our bx is going to be here, our by will be here, and our bz component will be here. And we're taking the determinant, which indicated by those straight lines. And so the way that we do this is it's a Laplace extension, I suppose. And what it's going to end up being is you're going to multiply here I'll write the extension for you, I suppose. So this is going to be equal to the determinant of ay, az, by, bz, and this is going to be multiplied by I hat, and then subtracted from the determinant of, let's see, ax, az, and then bx, bz, and multiplied by the j hat. And like I said, if you've never seen any of this, don't worry about it too much. It's just linear algebra. And then we're going to add this to the determinant of ax, ay, and bx, by times the k hat vector. And what you should end up getting, if you recall how to take a 2 by 2 determinant, you can multiply these two together and then subtract after you multiply these two together. So what this will end up being is ay, bz, so ay, bz minus az, by times the I hat component, and then we're going to subtract here, so minus ax, bz, if you're looking at the j hat component now, ax, bz minus az, bx, and that's going to be multiplied by the j hat component, and then we're going to be adding to that the final determinant, which is ax, by, so ax, by minus ay, bx, there, and that's multiplied by the k hat component. And so this is going to give us our vector. You could also write this in the vector form. You could write it as this aybz term, which I'm just going to represent with a little tilde. So aybz minus azby, that's what this tilde is. So this here is tilde. And then we can have a star for this one. This one can be a star. So this one is a star. So star. It would have been better if I had just represented these with letters, but since I'm already doing it this way, then I'll just go ahead and call this one a triangle. Or you could have called them, alpha, beta, and gamma, or something if you had wanted. And you could write it in this form as well, and this is just a vector where this is this tilde is the I hat component. The I hat component is the first part. So this is the I hat, this is the j hat, and this is the k hat. And so this is the vector that is output by the cross product. I had mentioned before that the cross product is also called the vector product because its output is a vector. And it's perhaps a little bit more complicated, a little bit less intuitive than the dot product, but computationally I don't really think that it's any more difficult. It's just, you know, a little bit of addition and multiplication and subtraction. So nothing that you guys can't handle. And one more thing that I do want to mention is that this vector output, so this, you know, this I hat, j hat, k hat, or this tilde star triangle, this output vector is actually going to be orthogonal or perpendicular to both of the input vectors. So let me write that down for you. So if A cross B is equal to C is a vector. You know, I just realized actually at the beginning of the lecture when I was saying that A cross B equals the length of A times the length of B times the sine of theta in between them. What I actually meant here was this is supposed to be the magnitude of A cross B, because clearly this is not going to be a vector output. So I'm sorry about that. This is the magnitude. This is the formula for the magnitude of the vector product. The formula for just a vector product is this A cross B term, or this C. This C is the vector that I had written down before as a tilde, a star, and a triangle. So that's the output vector C. And the output vector C is going to be orthogonal, or perpendicular in other words, to both of the other vectors, to both the vectors A and B. And so what that means is that it's, let's just consider a very simple example here where we have, let's say we want to consider the cross product of this is our x vector, so x and y. Actually, I think I got those backwards. This is y, sorry. This is y, this is x. And we want to know what x cross y is, where x is just 1, 0, 0, and crossed with y is just 0, 1, 0, 1, 0. Well, this very simple example here will show you that this is actually going to give you the vector in the z direction, so the k hat vector. So this is going to equal, you can go through and do the math, this is going to equal 0, 0, 1. And so what that means is that vector, this 0, 0, 1 vector here, this is going to be perfectly in the direction of the z-axis, perfectly in the k-hat direction. And so you can see that it is actually, in fact, orthogonal both to that y vector and to that x vector. And that is, in fact, going to be true for any cross product. You can use something known as the right-hand rule to determine the direction of it, where if you take your right hand and you kind of curl your fingers around, so curling your fingers from this x to this y term, you might have heard of this. It's a little bit difficult to explain when you can't see my fingers, but you're going to curl your fingers in that direction, and then your thumb is going to point in the direction of the resulting vector, so in the direction of the c vector. So your thumb is going to be pointing, if you do this, it's going to be pointing straight up. This is the direction of your thumb, so you know that that is the direction of the resulting vector. And similarly, if you were to consider y cross x, so if you were to consider y cross x instead, you can see that using the right hand rule, you're going to have to flip your hand upside down to do this, but you're going to curl your fingers from y to x now. You'll curl them and you'll see that it actually points downwards, which is its direction is the same but the opposite. So that is minus 0, comma 0, comma 1. So that actually serves to, I suppose, kind of reinforce, although I still haven't proved it for you, like I said, I'll do that next time, but reinforce the property that I mentioned to you earlier, that A cross B is equal to minus B cross A. And yeah, that's all that I have right now for the vector product, but be sure to check back again, and I'll have those proofs up for you. All right, have a nice day.